All right, welcome to the Friday Transportation Seminar at Fresno State University. I'm Elizabeth, professor of civil environmental engineering. I'm one of the instructors for the course. The other instructor is Dr. Aaron Dahl, and for the urban planning section. Before we start the seminar today, I have a few quick announcements and reminders. Because we have changed, as you've attended before, we've changed the process a little bit. So first of all, there's a sign-in sheet going around. For those of you here in the room, please sign in. Remember, everyone, to please submit your questions on D2L, regardless of whether you ask it in class or ask it online. Everyone needs to submit to D2L. If you're watching remotely for class, you need to be logged in for the entire hour. So you actually have to watch the seminar. And you are allowed to miss class one time during the term and watch the archived version of this. You must submit your questions before Tuesday following that. So, any questions before we get going?
Last week, the friends would find the right place to see these questions.
Yeah.
And I think I found it somewhere, but it had dates for last term.
Yeah.
So
on D2L.
On D2L.
Yeah, no worries. You just, I have everybody, the two people stuff. And that way you can change the date. Okay, well, our speaker today is Dr. Miguel Filiosi. He is a professor of civil environmental engineering. And if you've been paying attention to the transportation landscape, it's really changing a lot. And so he's going to talk today about one of the big changes that are happening, which is the prospect of thinking about delivering freight by drone. So,
okay.
Yeah.
Thank you, Kelly, and thank you for coming. Today, my talk is about drones, so this is a fairly new topic. If you have questions, I'm happy to, answer questions as I go. So, if you have a burning question, no problem. Just going to see if we can get it started. It's not working now. It was working before.
I broke it. I'm so sorry. Let's see.
That's all right. Okay. So let's start with a quick motivation. So this idea about using drones, it's fairly recent, and I guess we're all familiar with some of the reasons why this might be attractive. So basically, we are running out of space on our roads, are very congested. It's very hard to find parking sometimes for delivery vehicles. It's very hard to actually, it's expensive to, find parking, then to have, a driver to go deliver a package and so on. So there are many reasons why, from an economic perspective, it would make sense if it's possible to use drones for delivery. We'll talk about some of the issues, but in terms of what would it mean in terms of if drones become, available as kind of common way of delivering, yeah? So just the other day, I heard that one number about saying it's projected, I think in China now there are people receiving 2 packages per day, per month. So imagine that as this grows, if everybody is receiving several packages per week, and even say 10%, 15% of those are by drone, it will be a fairly, large number of deliveries. We'll be talking about millions of deliveries. So it's important to think a little bit about, well, what would this mean in terms of environmental impacts? And that's what I'm trying to talk about today. There is a lot to cover in this topic, but I'll just focus on the kind of sustainability emissions impacts. So the idea is, some of you might not be familiar with supply chains, but typically a supply chain is this idea about products get to your house, but first they raw material has to be usually, shipped to factories, then to warehouses, then assembled, then to more warehouses, then to distribution centers, and eventually they go to a consumer, yeah? So there are many kind of, I would say, legs in this supply chain. And typically what we are talking now about drones is basically looking at this kind of the last leg of the supply chain. So instead of using a delivery van or a truck, we are going to assume that we're going to be using a drone for that last mile of the delivery. Yeah. So this is kind of a shift, not in the whole supply chain, only in the last leg of the supply chain. So a little bit of a recap in terms of what is known in terms of academic publications regarding drones. When we started working on this, honestly, there is almost nothing in terms of what it means for transportation and logistics. There is a lot in terms of the electronics and in terms of technology, in terms of what people in computer science or electrical engineering are developing in terms of controlling drones or getting better software or hardware. But in terms of what it means for transportation logistics, there is still, a very kind of big gap in terms of knowledge. So the first thing we did was to, in a way, try to survey the type of drones that were available in the market. So we did kind of an extensive internet search. And because this is a kind of pretty new topic, information is not standardized, so it was pretty difficult in a way to make sense about what is available. But at the end, we collected data from 21 UAVs, unmanned aerial vehicles, also drones. So I use drones, but the technical term is UAV. And, we kind of focus on trying to get a range of drones, specs from the very small ones to the kind of, the ones that would be able to deliver a package. So just to give you a sense about what kind of drones we were surveying, looking for. First, we focused on multi-copter drones, and those that can be potentially used to deliver things in urban and rural areas. And because we wanted to also think about urban deliveries, we narrowed the search a little bit. So basically, we didn't include drones that are just helicopters, basically one propeller, because the size of the propeller is such that it would not make it safe when they are in close contact with humans, or property. So the other thing is we didn't include fixed-wing drones because they need a special kind of requirements or special facilities for landing and taking off. So it's not possible to have in an apartment building or in your backyard, typically, the infrastructure that you need for this type of drones. They are, for example, being used in Africa to deliver medicines or blood supplies and so on. So it would not be feasible for a kind of, dense urban area to have this type of drones. And the other thing was we also limit the search to electric ones for two reasons. One, because in urban areas, the electric ones are noisy, but, they are much noisier, the ones that use combustion engines. And also for, environmental reasons, you have an extra burden of burning fossil fuels in the case of the other type of drones. So we kind of limit the search this way. And this gives you some example about, I wanted to include this picture just to give you a sense about the size of the drone that, for example, DHL in Germany is thinking about. And it's nice to put it in context, here in relation to some person that in this case is carrying the drone. And what I mentioned before about having 4 propellers instead of if you had 1, imagine that the size of that 1 propeller would be, you would not be, want to be near that one, yeah? But you see it's kind of, considerable size if you want to carry a package. And that obviously has some issues in terms of how you deliver, in tight, small spaces in urban areas. So this was the kind of, type of drone we were thinking about in terms of our survey and our model that I'm going to present. So I'm going to give you, there is a wide range of capabilities just to give you some idea so you get a flavor about, what drones can do today. So in terms of speeds, they are actually pretty good. So they can have like cruise speed between 30, 40 miles per hour. So if you think that roads or streets are congested or you have a lot of traffic signals, if you are able to fly at this speed of 40 miles per hour without stopping, it's great. It's very competitive. Yeah. The flying times, though, and this is related to battery, they are still not great. They are mostly limited to 20 to 30 minutes. And that kind of also, if you combine the speed and the flying time, give you a sense about the range, yeah? Because the drone will have to go and come back and still have a safety margin. And that kind of, we are talking about nothing beyond 10 to 20 miles, but then that range is also a function of the load. So the heavier what you want to deliver your package, or the bigger it is, the range will decrease too. So it's kind of pretty complicated. There are many factors, but just giving you some idea. And again, the payload, roughly you think about 2 to 6 kilograms, 4 to 14 pounds. So size and weight, and again, this is kind of important in terms of considering what is feasible in an urban area. The average size across the diagonal, so we're talking roughly 1 meter, yeah? So 1 meter in terms of just the diagonal of the frame, yeah? You have to add the propellers. So the size is, it's not tiny. We're talking about things like this at least. And the takeoff weight, so one thing is the payload, but then you have to add the weight of the frame, the propellers, the engines, the batteries, and so on. So it could be, from up to 10, 15 kilograms, yeah? So we're talking like up to, 30 pounds, yeah? You need to think now that also, if you have 20, 30 pounds traveling at 40 miles per hour and they crash, can have a safety impact. But we're not focusing on safety today, just looking at sustainability. So I'm going to go back to the topic and the cost. Again, maybe you got for Christmas one of these tiny ones, could be $100, but the ones we are talking about delivering something around 10 pounds, you're talking like, $20,000 to travel, like say 20 miles, yeah. So it's a wide range of costs that are associated with, what you can do in terms of payload and travel distance. So just to give you a sense about what is the configuration of a good drone for deliveries, like the ones like, for example, DHL was considering, and one of these kind of, typical old-fashioned vans that we can see as a service utility vehicle in the US. So we have 4 rows here, the gross weight. So you see like, 15 kilograms versus 4,000 kilograms. So we're talking about a big order of magnitude. The same thing with the curb weight. The payload, again, huge difference. And the maximum range, again, very, very different too in terms of what you can do with the maximum energy that you can pack into the vehicle. So what I'm going to compare now I'm going to start this presentation with the simplest case. So imagine that for that last mile delivery, that last leg from the hub or the distribution center to the customer, we use a drone. So we have to take off from our distribution center, go to the customer, and come back. So one drone serves one customer round trip. The comparison here is then against using a small van to go from the distribution center to the customer and come back. So the van just goes, again, one way, and then come back. So it's the easiest possible case trying to compare the two vehicles. So what we're going to see here is that the energy consumption, assuming a package, say 5 kilograms, roughly 10 pounds, that the energy consumption in terms of watt-hour per kilometer, we're talking about 21 for the drone, and we're talking about 1,000 for the van. Yeah. So if you're just delivering one small package, it's clearly that in terms of energy consumption, the drone is much, much more efficient. Yeah. And again, this taking into account that we have much less energy, so we need to deliver that. We are comparing within this 20-mile range. Yeah. We cannot go beyond that because then the drone would not be able to compete. So the drone is limited to a fairly kind of a small area around the distribution center. But anyway, it's more efficient in terms of energy consumption. So per unit distance, the bottom line, just so you want to remember a number, we can say that around 50 times more efficient in terms of per unit distance to deliver one package. Yeah. So why? Just because it's all comes back to physics, and basically the problem with the van is that you have a very heavy vehicle to deliver a very tiny package. So it's just all that energy to move the heavy van compared to the light drone is what makes this ratio of 50 to 1. Yeah. Moving on the ground requires less energy if you have vehicles of the same weight. But given the big difference between the weight of a van and a drone, the drone ends up being more efficient 50 times. So, but that's assuming kind of the best case scenario for the drone, yeah? But now if we think about, well, what happens now if the van is full of packages and the drone has to, go and come back, like say 400 times, yeah? So then the van becomes 8 times more energy efficient, yeah? So if we are considering the full capacity of the van, then the van is more efficient, 8 times more efficient. If you are considered just one package, the drone is 50 times more efficient. So clearly there is a break-even point in between the two extremes, yeah, because we're considering the two extreme scenarios. So this is just talking about energy. If we are talking about sustainability, we can also add a factor related to emissions. In this case, emissions related to the energy source. So the van uses typically diesel fuel. So there is a carbon footprint associated with getting that diesel to the gas station where the van is going to get that fuel. And there is a carbon footprint associated with the kilowatt what is being charged in the battery of the drone. So these numbers, you can look at the statistics, like say for the Pacific Northwest in terms of given the energy mix in terms of the generation we have here in the Pacific Northwest in terms of gas, coal, hydro, nuclear, and so on, you get some carbon footprint on average per kilowatt hour. So we can take this into account and then add it to the calculation. And what we see, using numbers associated with our region, we see that in terms of the emissions associated with the energy source, for the electricity, we have 1.23 pounds of CO2 equivalent per kilowatt hour. And then if we look at the fuel, we get the emissions just associated with moving that gallon from the origin of the, the oil fields to the refineries and so on is 5.1810, and then we have 22.7 associated with burning that fossil fuel. So if you look at these two numbers, they are roughly 28 versus 1.2. We see that in terms of emissions, the drones will be much better, per kilowatt hour of energy consumed. So then if we multiply, then we get 10.8 and 10.16 watt-hour per kilometer. If we apply these coefficients, then we will end up the per unit distance, the UAV is roughly, again, another easy number to remember, 1,000 times cleaner in terms of CO2 emissions. So this is just combining the energy efficiency with the carbon footprint of the energy source. So this is telling us that, again, to deliver one package is much better to use drones if you have to deliver just one. But again, if we are assuming that the van is fully loaded, then we are talking now that the van is almost 2.7 times less efficient regarding CO2 emissions. So this is just using this van. Again, this van is not the most efficient vehicle in the market, but I'm just using it now to give you an idea about what is comparing against this type of vehicle. But I'm going to present more efficient vehicles later on, and you will see that the numbers are going to change. So in terms of CO2 against the not so fuel efficient van, even when it's fully loaded, the drone is better. So now we're going to move to a case that is slightly more complicated. So instead of assuming that we have one-to-one deliveries, we have now what we call one-to-many. So the van can go from the warehouse and then deliver to end customers. End could be 50, could be 100, could be 150, whatever it is, what is allowed given the the number of hours that the driver can work and so on. So because now the van can combine customers, it's going to become more efficient. So in terms of always, on average, as the number of customers per route increases, the distance traveled per customer is going to decrease. So every time we add a customer, on average, the van becomes more efficient. So all the formulas are in the paper, so I'm not going to show any formulas, but if you want to check the numbers, it's all there in the paper. For the sake of time, I'm not including any formulas in the presentation. But what I'm going to present now are tables where we are looking at energy efficiency break-even points. So basically, I'm going to show you numbers where the drone is equivalent to the van for a given set of conditions in terms of energy efficiency. So let's see how we can understand this table. So we have 5 columns. In one column, in the first one, we have the average distance from the depot to customers. So first row, we assume that is 8 kilometers, roughly 5 miles. From 8 to 12. And in the second column, we have service area, so the area that can be served. And these two columns were chosen in a way so that we are within kind of near the maximum range of the drone. Yeah, we are combining average distance and service area so that the drone is within a feasible range of service. Yeah. So these two relate to the geometry of the delivery area, and then we have three columns. So here I'm assuming in this fourth column, 21.6, that is kind of what is estimated that average efficiency for this type of drone that we have chosen. But there could be a lot of variability in terms of energy consumption for drones, depending on the wind, depending on flying conditions, and so on. So there are also two other numbers. One here on the third column that is half of this one. So assuming that it's much less efficient, basically by order of 2. And then in this last column, 32.4, basically 50% better in terms of what can be consumed. Yeah. So then how do we look at these numbers? So basically here we are saying that for a given set of conditions, say average distance to the customer 8 kilometers, service area 60, we would need 1340 deliveries per van to have the 2 break even. Yeah. And as the distance grows, then these numbers go down just because per unit distance, the drone is more efficient. So as customers tend to be farther away, the drone has an advantage. So you have this distance that number of customers is going down. So then here we have how it's changing with the different efficiencies that we assume for the drone. So it's going from higher to lower. So just keep the order of magnitude, but just to give you some reference point, what do you think is the average kind of in an urban area, like say Portland, inner suburbs or downtown, how many packages per UPS van are delivered roughly? Packages. Yeah. So it could go from, 200 in kind of dense areas to 100, less in rural areas. So that keeps, it tells you that somewhere in here, for like in a dense area, there is a break-even point that relates to what is feasible in with the kind of the number of deliveries that packages can be done with the vehicle. But, that's kind of assuming kind of high efficiency, saying 200, 300 deliveries. But in many kind of more suburban, more isolated areas, the package delivery services cannot put so many packages in one vehicle. They are less efficient than that. So just moving on a little bit, I'll tell you that I was using a van before, like not great in terms of energy efficiency, but here now I'm using an electric van. This is a new kind of 2018 model Renault electric van that is available in Europe, not in the US, but it's a very efficient electric vehicle that can be used for deliveries of service calls in urban areas. Yeah, and I didn't include the picture here, but I'm also comparing this with the efficiency of an e-truck. Yeah. So how do we read these numbers? So let's say that the average distance from depot to customers is 8 kilometers, service area 60. Then using an electric truck, you will need to deliver 214 packages to break even. But now, if you have an electric van, a much smaller vehicle than an electric truck, you only need to deliver to 26 customers to break even. Yeah. And if the distance is longer, then you get to even down to 10. So again, let's think about that 200, around 200. That's a good, very good number for a UPS vehicle to think about what these numbers mean. Yeah. So then we are lucky to have here in Portland B-Lane, that is a tricycle, human electric power delivery vehicles. You might see them. They service, campus, and office buildings around downtown. So we did some study, with them, and we got to, measure what is the energy efficiency of these tricycles, starting from the depot on the east side to deliver here to downtown. And then if we do the same thing, we compare a drone versus using a tricycle, then we see that only having 2 customers, 2 deliveries, 2 packages using a tricycle, that will break even with the drone. Yeah. So meaning that if you deliver 3 packages using a tricycle, then you are more energy efficient than you would be with a drone. Yeah. So, and in this case, with electric vehicles, that issue about the carbon footprint, it doesn't change because now they are both using electricity. So before, when we were comparing with the diesel van, we had to add that penalty for the carbon footprint of diesel. But here, because we're comparing electric with electric, we don't need to make that adjustment anymore. Yeah.
I was just wondering, when you look at the energy efficiency of those tricycles, do you also look at like the extra calories burned by the individual operating it as far as factoring in?
Yeah, that's a good question, but we didn't. And we didn't for the reason that we were just measuring, from the battery before and after, what was the actual, kind of consumption. And the thing is, if we start taking that into account, then you can say, well, there is a health benefit too. And there is, so if you kind of start adding more things, but yeah, we did. So the short answer is no, but the long answer is we didn't do it because then you will need to consider many other things if you want to be fair in terms of taking that into account. Yeah, but but the kind of the riders, they kind of contribute like 1/3, depending again on the size of the rider, how if they're how fit they are, how strong, they could contribute more or less. But there is they do they provide some of the energy, but it's not the majority of the energy. So again, thinking about the typical delivery van, we're very far from those numbers now in terms of break-even point. So there is one more thing that when we are talking about sustainability, we need to think about, and that's kind of the life cycle of the vehicle. So in terms of, we can, it's fairly easy to think about just the energy and the CO2 associated with that energy, but then you need to think that to manufacture that vehicle, you need to use energy, for the materials, for assembling, and so on. So there is a lot of energy that is necessary to create a vehicle. So in that sense, people have worked on this life cycle analysis that you can take into account all these different components, and then you can get the statistics for the typical vehicle, what is the carbon footprint of manufacturing, but then at the end, you also take into account disposal, because there could be elements like, say, the battery, given the metals and some of the processes that are required, may be harder to recycle than other things like, say, steel or aluminum or other materials that are used. So it's kind of, it's a topic on its own. But if we take this into account, then we need to, think about, make some assumptions about, you're having this, you have to kind of, in a way, kind of divide these kind of vehicle emissions over the life of the vehicle. So in this case, we assume on average 4 deliveries for the UAV, 25 for the tricycle, that's kind of what we see in Portland, and for the van 150. And then assuming that vehicles operate 52 weeks, 5 days a week, and then you have different lifespans in terms of what the vehicles are likely to last. Again, we don't have enough information about UAVs. We have pretty good information about other vehicles in terms of what is the life of them. So making some assumptions here, we can get these numbers about emissions per delivery. So then you see that in terms of the vehicle CO2, the drones have a much higher, kind of contribution in terms of the vehicle itself. So if we put this in equivalent travel distance, then we see that, that kind of, it's pretty high for the drone. So meaning that the vehicle component for a drone delivery is roughly like, flying 13 extra kilometers per delivery, yeah? But it's tiny for the other vehicles just because they are used so much over 10 years, yeah? They are used much more. That's why, even though they are bigger, they are used much more over the lifetime. So the contribution of manufacturing the vehicle becomes much smaller. So then finally here, the equivalent travel distance as percentage of the range, and we see like here is 52% versus, pretty much 0 for the van. So just to wrap it up, and I don't want to talk for too long. So just summarizing, the drones are great in terms of low energy and low CO2 emissions per unit distance. So if we are talking about delivering one package or one thing in a remote area, it's much, much better to use a drone than to use one ground vehicle. Even if we take into account this, the vehicle phase emissions. But in terms of deliveries in areas where you can have routes with many customers per route, then the UAVs are not as efficient, and then we saw there is a break-even point where they become less efficient. Yeah. So for urban deliveries, compared to a well-used delivery tricycle or electric van, or even in some cases an efficient diesel van, drones will not be more sustainable. But again, that's assuming a lot of high efficiency on the ground vehicles. So just wrap it up. I'll go very quickly. So I mentioned all this, this an analysis done based on the vehicles, but as you know, nothing is being delivered yet, in a kind of massive, basis to customers. So there are still many, many logistical barriers to consider in terms of, for these drones to be implemented, in terms of how the actual kind of, not the last mile, just the last yard of the delivery is going to happen, safety issues. And then, the payload, again, is a big limiting factor in terms of what can you deliver up to that amount. And again, the drop-off, well, there are many, many startups and people thinking about different options, but no one has still come up with an idea that regulators are happy to say, yes, this can move forward, and become a massive system. I'm not going to talk about economics. We're running out of time. But I want to mention that another issues that are still important and pending is the traffic control. So if you think about this system scaling up in terms of drone deliveries, we have traffic signals for controlling our streets. You would think that it's necessary to have a system that would coordinate all these vehicles to avoid, crashes and issues in terms of safety. So that's still a big issue. Again, potential, like with any autonomous, vehicle, ground or airborne, there's still issues in terms of liability or what may happen when something goes wrong. So energy, again, I think the future of drones is for urban delivery is going to be electric. And then, there are other things in terms of, it's not very clear yet in terms of how people are going to react in terms of if this becomes, widely available in terms of the noise, the privacy issues, and so on. Still not clear what's going to happen. But for sure, technology is improving very, very fast. Yeah. So batteries and the drone, itself, there are just these vehicles are becoming much better. That's something we know for sure. So if you want to see, all the details and formulas and so on, the paper is on my website. So go there. We have other papers under review. And also posted there other papers related to the efficiency of electric trucks and tricycles. So they're all available in my website. And finally, I want to acknowledge the help of two PSU students, Chuck Tucker, his help with the survey, and Paulina also, helped in terms of validating some of the data. So thank you to all of them. And I have to acknowledge the funding from this for this research was provided by the Freight Mobility Research Institute. They have been supporting the research I have been doing regarding drones and robot deliveries and innovative ways to create solutions for the last mile. And with that, I'm happy to answer questions. Yeah.
So I have a question. So typically when trucks are making these deliveries in urban areas, are they just doing deliveries and not doing pickups too, or are they multi-function in that way? And then if so, how much complexity does that add to your analysis?
So I think it's a good question. So different companies may operate in a different way. There is not just one recipe. So some companies operate in a way that there is kind of a deadline for, say, well, you have to, if you want to have next day delivery, you have to drop off your package by 4 p.m. or 5 p.m. And then, maybe then some vehicles can deliver, and on the way back, they can go to the collection points and take, some packages back to the hub or the airport. But that's, it depends on the city, on the company, and the geography in terms of, pickup and delivery points. So the answer is possible, but it's not like all people.
Do you know if you said that electric vans and vehicles are more used in Europe? Do you know if they're subsidized, if their use is subsidized by the government, or if the companies have motivation otherwise to use vehicles?
So I think Europe has a couple of things going for these EVs. One, fuel is much more expensive, so that makes a big difference. And they have higher taxes and more regulation in terms of cleaner downtown areas. So, for example, in Paris, they're just saying, well, they are not going to allow more diesel vehicles. Yeah. So it's in terms of the regulatory framework, just because they have more issues in terms of congestion and emissions and so on, they are much tougher. So they have an environment that is that makes the kind of the economical analysis make it much better for electric vehicles.
And just a reminder to recast the question in the cache. You want that short time here.
Oh yeah, I totally forgot about it. Yeah.
I have two questions. Is it possible combine the drone and the van, like the aircraft, the carrier, to track them, for example, move the classroom and drone view and optimize the results? Second is, it seems like this building environment, the drone have not a lot of advantage. So my question is, do you think a suitable density is for better for drone? Above this density is not advanced.
Okay. Thank you. So 2 questions, and then reformulated so people in the online audience can hear. So if I remember correctly, the first one was about having a kind of hybrid system where you have a conventional vehicle and then a drone. And, you know, that's being tested, and, you know, that's actually can potentially, if, you know, in some situations, you can combine the best of the two. So you can, you know, maybe travel with your van, carry many packages and several drones, and then, you know, have the final delivery to locations that are not easy to access. So, and that would be, you know, that kind of trying to combine the best of the two systems would increase the efficiency even more. So, but again, all the conditions have to be met, so you get this kind of multiplicative, you know, kind of efficiency. So that's definitely something that, you know, that I didn't consider, because it would add one layer of complexity, but definitely would change the numbers. The other, I think the other question was more related to the, you know, that kind of final, that last yard of the delivery, and what is better in, you know, and thinking about urban areas. So, you know, some people are thinking, like, say, the rooftop of buildings, you know, say, well, instead of accessing, you know, traditionally, you know, through the street, the sidewalk, you could, you know, kind of somehow, you know, modify the rooftop so you can have a delivery area, you know, for drones, you know, and that would be great if it's, you know, can be done. And so basically kind of having, you know, a small kind of mini kind of drone airport on top of the building, you know, and that, given the size of these vehicles, you know, it would not require a lot of space. So there is a lot of kind of research and thinking going into that, and that would be kind of ideal for dense areas, like, you know, you think about Tokyo, Manhattan, you know, very areas with very high density and with very tall buildings, you know, that would be a great solution. Though, you know, if you're talking about just your backyard, you know, like my house in Southeast Portland, where, you know, I have a small backyard, well, that's much tougher, just because you have trees, you have power lines, you have all these kind of obstacles, you know, in terms of how, you know, how economical would be to have just one delivery area, you know, so it just kind of, that's, you know, it's also a tough kind of, you know, a tougher environment in a way to think about, you know, deliveries. You know, people are thinking maybe about having kind of neighborhood stations where, you know, drones can go and deliver, and, you know, with the smart technologies, like, you know, like you can go and have a locker, you know, where, you know, someone can be kind of unloading these vehicles and putting things in lockers. But, you know, again, that would require kind of a system, you know, that is not in place today. Potentially there are a lot of great ideas, but it's hard to know which one is going to win. So, yeah.
So 2 questions. In your paper, do you go into more depth about the economics of it? And then on that, just because with drones, they seem to be, they're more susceptible to weather. And so how does that affect, you know, you have a couple days of bad weather, how does that affect delivery companies? So wouldn't that kind of reduce the incentive for them to use drones?
Yeah, so I'll rephrase the question so people can, I think they can hear you, but just in case. So I think in terms of the economics, the paper that is published is just about environmental impact. The one about the economics is under review. But I can tell you that what makes a big difference is, you know, is the kind of the human factor in terms of now current regulations assume that you have to have you have to fly within line of sight. So basically, you need to have an operator for each drone. So basically, you need to have someone, paying someone to be kind of, managing that delivery for each delivery. So that means that basically you're paying, if it takes half an hour for a delivery, you have to pay whatever you pay, $30 an hour, $15 for someone to just, kind of oversee that, that everything is done according to current regulation. But what companies are thinking in the kind of best possible ways to have the kind of really unmanned, but also kind of autonomous in the sense that there will be maybe one person controlling 100 drones. Yeah, so then that would change, completely the kind of economic equation in terms of the cost of delivery. Yeah, so that's one of the huge factors. And I'm trying to remember what was the other part.
Just how drones are susceptible to bad weather.
Yeah, so that's I didn't mention that, but there is, depending on how stealthy is the drone, there is a maximum wind speed that are allowed to, they can safely operate. So in terms of very windy places, you would have to assume that several days, throughout the year, they would not be able to operate. So companies will have to have the kind of backup system to, to deal with those situations. So that's, it's something that, again, it's this trade-off between operating conditions and has a lot to do with the size and how stealthy is the drone. But I think that also kind of gets into the safety side in terms of if they are heavier, bigger, then they are potentially more risky in terms of when they crash. So, again, there is a trade-off in terms of that the regulation will have to eventually, set the kind of the boundaries about what companies can do, and I think, based on that, they will, develop their systems. So I think there is still the kind of the regulatory kind of framework in terms of the specifics, still kind of up in the air. So I think once that is kind of, established, then it would be easier for companies to think about, well, what kind of systems or what kind of complementarities you need to have in terms of vehicles to ensure deliveries when, conditions are not optimal. So that's a great question, but, still, it's hard to answer that one, with the current kind of information that we have.
Okay, so it seems like batteries are playing a big role in affecting the limiting edges of a lot of the things that you're looking at, both in terms of energy storage, energy density and weight, and then also the environmental impacts of producing and disposing of them. I didn't see the breakdown, but I assume that that was one of the main reasons that drones are so much higher there. There's a lot happening in that industry. Do you foresee those numbers changing in a meaningful way that would upset the way that this equation balances now in the next 5, 10, 20 years?
Yeah. So, yeah, that's a great question. The question is about, the changes in technology and how is that, potentially affecting this sustainability of drones. So, as technology gets better, they will be able to do more, with less energy. So that's great. And we would have smaller batteries, or maybe have the same weight of the battery, but pack more energy per battery. Though the issue is that when these drones have to be, if it gets a bit complicated because then you have recharging time. So if you want to use a drone, have high utilization, you need to have more than one battery. Yeah. So you need to have maybe 2 or 3. Yeah. So then, in the paper, I was making an assumption that at least, you need to have at least, 2 batteries, but that's also an issue in terms of how quickly, you kind of the turnover of the batteries and the cycle. But what happens with batteries too is that as they become better in terms of active more energy, it's not clear that the environmental kind of impact diminishes. Actually, it could be that the materials and the processes are becoming more onerous in terms of disposal and recycling and so on. So it's not clear. The trend is clear in terms that the batteries are getting better, but in terms of getting better in terms of emissions per mass of battery, I think that's very uncertain, and I honestly I don't think no one really knows, because for this analysis to be done, you have to. It's pretty complex, and and so I think it's an open question. It's a great question, but. Anything else? Yeah.
I have it's kind of a three-part question, but mostly how feasible would this actually be to implement in the US, and what kind of systemic changes would have to be considered? And is there kind of like a rough hypothetical timeline of something like this being put into practice?
So I think there are two questions. One is, so how feasible is the first one? Well, I think the feasibility, so currently now with the regulation, it's not possible. Yeah, so because you need to have like a site, and then each company will have to request a waiver from FAA, Federal Aviation Administration, and so for kind of urban deliveries, I would say that it's not possible now with the regulatory framework. For kind of more deliveries in isolated places or testing, in kind of remote areas, that's feasible, and that's what companies are doing. So in terms of when the regulations are going to change, well, it's not clear. NASA and several companies are working on some framework and some kind of control system, air control system, to kind of manage a large amount of drones flying at the same time. That's being developed, but has not been fully tested, and it's never been kind of implemented either. So you would think that there is still some kind of steps that have to be taken before that the system is kind of tested, making sure it works well, there are no bugs, there are no issues, no problems, and then you would think that after that, maybe some, again, I think people from NASA, reading the other day, they're thinking maybe 2 or 3 years they can deploy a system, test it, and so on. But you never know with this kind of this is very kind of uncertain kind of type of project, because you don't know what are the actual problems they're going to face in actual urban environment. Again, with power lines, birds, objects, or people, flying things, not following the rule. It can, so we don't know what would be the kind of how messy it would be. So in that sense, I think it's hard to say when. But there are governments that are a little bit more open in terms of regulation. And so other countries like Australia, UK, that are a bit, experimenting a bit more. Australia, makes sense. They have huge, isolated regions, so they are really, testing a lot more in that sense, but not in the dense urban areas, but much more in the kind of outback. So different countries are trying to regulate and to set limits in terms of safety and so on, but it's a very fluid and very dynamic kind of type of environment. All right.
Well, we're out of time, so let's thank Miguel. Next week we have Joe Broach, who is a researcher here at PSU.